Hi, today I'm going to be talking about our Physics 2212 Lab 3 called Circuits. My name is Faisal Kasim, and let's get into it. So for this lab, the main goal was to investigate current and voltage using energy and charge conservation in series and transient RC circuits. And the main physics models we used were Ohm's law, Kirchhoff's laws, and exponential decay, which we used for the RC circuit. And a summary of the key results were the current is uniform, the voltage is summed to zero, and for the RC, the capacitor voltage decays exponentially, verified by the time we used, time measurements. For the lab setup, we used two 1.5 voltage batteries and two resistors, one 47 ohms and the other 100 ohms, connected in a single loop. The method we used for current was the ammeters were connected in series at points I1 and I2. And for the voltage method, the voltmeter connected in parallel across each component to measure the potential difference. And this is a tiny picture of what we did for the lab. As you can see, everything is connected the way that was explained in the slide before. After doing the lab, we took note of some of our main results. The measured current we got for the initial reading was 18.8 milliamperes, which as you can see is the same as the measured current at another point, which just proves KCL, that charge flows uniformly through a single path. And for the reverse test, we reversed the ammeter polarity and we got negative 18.8 milliamperes, which confirms that the direction of the current is different. And also, our potential difference was negative 0.552, just a little bit big, but the total loop sum was between 0 voltage and 0.2. We didn't have an exact value because it kept changing. And to verify this, our sum is negligibly close to 0, which means that KVL is confirmed. Kirchhoff's voltage law is confirmed. And a tiny error we had was the small non-zero sum is due to slight resistance in wires and instrument imprecision, because you can't exactly get a perfect 0. And for our RC circuit results, the bulb brightness decreased over time, confirming the current depends on the decaying capacitor voltage. So our charging time value was 1 minute and 19 seconds, and our discharging time was 1 minute and 1 second. And using the voltage and the time, we can plot a graph to show how current decays over time in a circuit. And for this lab investigation, we primarily utilized real physical and circuit components, including actual batteries, resistors, capacitors, ammeters, and voltmeters, which allowed us to observe non-ideal behaviors like wire resistance and component tolerance. So now for the what if question. What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, in the ideal circuit model where no resistor is used, the capacitor will charge instantaneously, taking 0 time. This prediction fails in real life. Our actual measured charging time was approximately 79 seconds. This significant difference is caused by the unavoidable internal resistance present in all real components, including the battery, wires, and measuring instruments. This hidden resistance creates a time constant in the circuit, which forces the capacitor's voltage and charge to rise exponentially over time rather than immediately, explaining why instantaneous charging is physically impossible. Thank you.